Thanks very much, Andrew. So we'll start, kick things off proper with session one. I am the chair of session one, so hello, I'm Wasim Al-Sindi, the managing editor of the Cryptoeconomic Systems journal. So the first session is called Cryptographic Economics 1, and the first talk is called Empirical Measurements on Pricing Oracles and Decentralized Governance for Stablecoins. And the authors are Wanyun, Catherine Gu, Anika, Raghuvanshi, and Dan Boneh, all from Stanford University. So hopefully they can join us. Hi, Catherine, can you hear me?
Wasim, I can hear you. Can you hear me?
Yes, we can hear you just fine. Can everybody in the room hear, or would you like a bit more volume? Okay, I think we're good. All right. Would you like to share your screen, Catherine, so we can get going?
Yeah. 1 second.
Fantastic, we can see that. Yes, go ahead, Catherine. Thank you very much.
Awesome, everyone. Hi, good morning, everyone. This is Catherine here, and together I have my colleague Anika as well. We're currently at Stanford, but I'm very excited to meet you all virtually. Thank you very much, MIT Cryptoeconomic Systems, for having us. Very excited to share with you on our paper. So our paper, Empirical Measurements on Pricing Oracles and Decentralized Governance for Stablecoins, is done by myself, Anika, and Professor Dan Boneh. And really would love to share with you some of the insights into the inner workings of stablecoins. Yeah. So just 1 sec. Great. So let's just dive in. What's a pricing oracle? Pricing oracle is basically essentially any type of mechanism that provides pricing data to dApps. An example of a pricing oracle could be a crypto exchange, an over-the-counter market maker, trader, or anyone who can provide reliable, good quality updates of prices. Now, there's a lot of decentralized finance projects out there, and pricing oracle is a very critical design, as many of you would appreciate. So here we only listed a few examples where we examine the protocols in our paper. They include the different types of stable coins, prediction markets, or voting schemes that all kind of make use of the pricing oracle. And it is incredibly important to have a pricing oracle which is incentive compatible, as we live in this decentralized trustless system in order to regulate people's behaviors individually. On the other hand, a vulnerability in the system when it's not well designed could lead to costly consequences. As you might know, that there was the synthetics platform attack that happened in June 2019, where about $37 million was being stolen. And similarly, quite recently, back in last month, the BZX attacks could, to some extent, be traced back to the oracle manipulation. Now, for our paper, we focused on MakerDAO as kind of our toy example and really look into the details of how the median is being computed and how the governance structure is being done. MakerDAO is one of the biggest DeFi platform out there. They have a stablecoin called DAI and was launched in December 2017. And for Maker, they need a pricing oracle in order to report the price of Ethereum. So from a very high level perspective of what is going on here is essentially, well, Maker has selected these 14 anonymous price feeders, and they interact with this on-chain medianizer contract, which then essentially is going to output a reference price for Ethereum, and that's what they call the median price. And from a very high level, basically, you'll just expect an array of prices being sent to the contract, and then it will just spit out one reference number. Now, we just want to dig in a little bit into the inner working of this median algorithm. And this is what we coin the forward fill rule. And you'll see very shortly how that forward fill rule would work. So let's just imagine at, say, 3 o'clock on the day, you have received all these fresh price reports. So for each price report, it is composed of two things. First, it is composed of the price of Ethereum that the price feeder fed in. And the other thing is this time parameter called valid until, denominated in hours. So for example, for feeder one, it's submitting a price of $200, and it's essentially saying that that price report would be valid for the next 6 hours to be reused in the computation of the median price. So from this array of numbers, we can just find the median of that array, and that's very straightforward. Now, interestingly, what if that 45 minutes later, and only price feeder number one has updated its price feed, and submitting a new price to the system, whereas everyone else is still being inactive within that hour. So everyone else's prices are showing the NA. Now, this is where the forward fill rule comes in, and essentially is asking this question: whether the price for each of these price feeders that was submitted back at 3 o'clock, whether those prices are still valid at 3:45 p.m. And to answer that question, basically, we just need to go back to that number for the valid until and subject them to the validation rule and trying to see if the number is still valid or not. And in our instance, because everything is still within the first hour, they all pass the forward fill rule. And because that's the case, the forward fill happens, and then we'll carry over the prices from the 3 p.m. and be put into the 3:45. And together, we'll be able to compute the new median price as shown here. So then let's just take another example where it is a little bit forward, more in advance, ahead of time. So at 5:30 p.m., again, there will be a set of new price reports coming in. And this time, quite a few numbers of price feeders have been actively updating the prices together with a new valid until number that they put in. Now, for those blank spaces, those are the ones that hasn't been active, and hence they have the NA. So this time round, before we apply the forward fill rule, we need to think about what's the valid until, and that's when we're updating the valid until number first. So between 3 p.m. and 5:30 p.m., there's a 2 whole hour that has passed. So what we need to do is first deduce 2 hours from all of these valid until, and then we subject them to the forward fill rule and ask the same question we asked earlier. And this time round, some of them failed and some of them are still passing that test. And for those that satisfy the forward fill requirement, the numbers will be forward filled. And using those valid price reports, we'll then be able to compute a new median price. And this is essentially how it works within the V1 of the MakerDAO system. Now, you would notice that at any time slice, we can only get at most 14 new data points just because we only have 14 price feeds overall in the system. And sometimes we might get fewer if some feeders are being active and the inputs have already expired. So that is what it's saying is that stale pricing could be potentially problematic, as you might imagine. Now, for MakerDAO, they introduced this 6-hour rule, and they said, well, essentially, any price report should not be anything that is more stale than 6 hours. However, even in our example, as you can see, we can specify something which is 8 hours, and then it will be carried forward. And this is fine because the valid until parameter is something that is being used and being provided by the price feeders themselves. They're not hard-coded in the medianizer's contract. So we'll see very shortly through the empirical measurements in terms of examining that 6-hour rule and other things. So let's move on to the empirical measurement side. And we look at the data of MakerDAO's platform for over 2 years worth of history. And there's a few angles that we look at. So the first type is the external disagreement, because essentially what we're trying to ask is how good is the quality of Maker's on-chain pricing oracle is. And this we can answer through empirical measurements. So we first look at the external disagreement between Maker's platform and a benchmark where we can compare the reference price for Ethereum between those two. Now, the benchmark that we have used for the purpose of our study is Cryptocompare. Cryptocompare is quite popular and is well known and being used by many people in the community. And the reason we use Cryptocompare's series CCCHGG is because they actually aggregate transaction data from over 70 exchanges, and they're computing something which is volume-weighted averages. And the price data that we got from Cryptocompare is actually multidimensional. So it contains prices which indicates the close, the open, high, and low, as well as volume information. Now, from this external disagreement, there's two very interesting observations we want to highlight. First is that disagreement can be huge, and it can be as much as $150, as you see there. Second thing is stale pricing does come into play. And in fact, the second biggest external disagreement, where there's a $67 price gap, that happens when 9 out of 14 price feeds were actually providing a price that's already 2 hours old. So The second angle that we study is the internal disagreement between anonymous price feed. And in this box plot, what we're essentially plotting is the average internal disagreement and the standard deviation on those internal disagreement. Internal disagreement is being defined as basically the price feeder's price report versus how the median output is shaping. And this chart is very illustrative in a sense. It's showing the idiosyncratic characters across different price feeders. Some of them are quite, having high standard deviation and reporting prices that's quite apart from the median. Some, like price feeder 14, is quite close. In fact, we highlighted some of them that are reporting very extreme prices. And feeder number 8 is showing the most in absolute terms in terms of the internal disagreement, which is up to 15%. Now, just in and by itself, it's very hard to tell exactly what's the causation. It's very difficult basically to carry any further investigation into that, simply because these price feeders are all anonymous. So we don't know if the deviation is a result of idiosyncratic characters. For example, it could be due to market liquidity constraints, or it could be differences in geographical distributions, or it could be a result of simply misreporting and this sort of malicious behavior that could be potentially there. So that's something that we can't infer just simply from the empirical data. Now, the last angle we looked at is sale pricing. And so this first chart is basically relating back to the valid until parameter that we described in the median algorithm. And this chart is measuring the expiry time of how long does those price feeders are specifying. So as you can see, initially at the launch of the median's platform, everyone is adhering to the 6-hour rule that is being imposed by the maker's platform. But then this was not carried forward throughout the entire history, and the 6-hour rule has not been enforced pretty much since the second half of 2018. In fact, many feeders are allowing a price to be valid for 12 hours. So what this is saying is that the price fees can be, theoretically speaking, be reused for up to 12 hours. Now, the next natural question, therefore, to ask is, what is it like in reality? I mean, how frequent are these price feeders actually reporting prices? And this is essentially what we did by asking that question. And you can get sort of like an answer on average by looking at the reporting frequency. And here's a histogram essentially showing how many price feeders are being active for 10 hours or beyond. Now, what the histogram is revealing is essentially, well, in reality, 0 feeders are actually behaving like that. And there's like 1 or 2 feeders who might be inactive for beyond 10 hours. And then in the end, on average, there's about 100 times overall when we do observe that 3 feeders are 10 hours stale or even more. So staleness definitely does exist in MakerDAO's V1. Staleness in itself is not necessarily a bad thing, because as you know, at any given time slice, we can only get up to 14 data points. So in a way, we want to get as much data points as possible when we're computing the median price. However, staleness does become problematic when we're in a period of market volatility. And when you have slow refresh by these price feeders, that's when you can see these massive external disagreement that we have observed previously. So moving on to the V2 version, which was launched very recently in November last year. There's a couple of new features. Firstly, they introduce additional collateral asset, BAT, into the system, and they also introduce more price feeders. And this time around, they're not anonymous, but rather public partners. We know their identities. And then there's this new Oracle module logic where all the median price computation takes place. In fact, everything happens on this median contract, which we'll now want to share with you the inner workings. So again, we have a list of price feeders. And then this time round, rather than sending information directly to the on-chain contract, what's going to happen first is these price feeders will interact with an off-chain relay server. And the relay server will receive a list of information like so. So these are all sort of price reports that's being submitted by price feeders. And each price report this time composed of 3 things: the value of the Ethereum price that they think is right, the age at which the price is being sent into the relay server, and lastly, the signature that is corresponding to the value and age. And what the relay server will then do is essentially sort everything by the value. And once they've sorted everything, they will produce this sorted array of values with corresponding age and signature. Now, at some point, this sorted array of numbers will be fed into the on-chain median contract. And this is just a bit of a code that we have highlighted. Now, the really interesting thing is actually the new feature built in this median contract to trying to address the problem with staleness, actually. And this is what we highlight. They have this requirement that says the length of the sorted array that's going to be fed into the median contract have to be equal to exactly the size of the bar. Now, bar is this indicating the size of the quorum, and is chosen by the governance. Currently, it is set to be 13. So that means we only want to have 13 price feed to be fed into the contract. And if anything is more or less than 13, then the entire operation of this poke function on the median contract will have to abort. So let's imagine what's going to happen is basically if you have more than 20 price reports, well, this off-chain relay server will sort out 13 of them and feed it into the median contract, and in the end compute the median number, which is the 7th in that sorted array. So firstly, the good thing about this new V2 version of the median contract is that staleness problem is definitely gone, because together with this requirement on the length of the sorted array, later down the code, they also have the requirement in terms of age. So in combination, they make sure every single price feed that is being fed into the median contract is fresh. Now, the problem with this, as you might already start thinking, is that firstly, in this simple example, 7 reports have already been thrown away. So essentially, we're discarding potentially useful price information that could be used in the median's computation of the median number. And second, because this relay server is sitting off-chain and they're doing all the sorting and selection of the 13 prices off-chain, there could be a potential attack vector happening. Imagining if the relay server is being corrupted and the selection process is trying to bias the outcome of the median price, it's possible that they can do that. And we think that is a potential bug in the code, and it would actually be better with our suggestion in terms of changing that requirement to be greater or equal to bar as opposed to be exactly equal to bar. Now, we just want to share with you the latest sort of results. So since November 2019, we have about 1,300 transactions that happens on the Ethereum contracts. There's the same amount of actually happen on BAT as well. But just for Ethereum, this is what we want to show. And for comparison, this is the external disagreement again. And it looks pretty good for version 2, because as you see, the maximum disagreement has only been $10. Now, there hasn't been a lot of disagreement yet, but because it might be a reason because the system is fairly new. So definitely worth keep watching and do some further work to analyze that. Now, the next part that we want to study is the governance structure in stablecoins. And again, we picked MakerDAO as our example to continue our investigation. And this is the part where my colleague Anika has done a lot of work on as well. And so here is an example of the governance dashboard on Maker. And in Maker's system, the MKR is the native governance token used. And one MKR equal to 1 vote. So they're using a proof of stake design. And for Maker holders, if they want to vote, then they need to lock up the MKR in the voting contract in order to carry out that procedure. There's essentially 2 types of votes: governance polls and executive votes. So governance polls is aiming just trying to find a resolution to a matter. Executive votes is a bit more serious because it changes the state of a system. Now, both type of votes actually use this style of voting, which is called continuous approval voting. And we'll just illustrate this by an example. So imagine the current state of the system has been executed under the current proposal, where you have 5 votes being contained there in total. And as a voter, what you can do is to transfer that vote from the current proposal to the new one. And this is what we call this continuous voting process. And you can continue to do so until that we actually have more votes in this new proposal than the current proposal. And this is when the new proposal will be executed and the state of the system will be updated as well. So essentially, for a new proposal to win, it doesn't need any majority voting. All it needs is basically to have more votes in the new proposal than the previous proposal. And that's that. Now imagine again that now we have malicious party that comes in, and they're trying to figure out how much vote would it take for them to win another new proposal. Well, if the current proposal contains all 5 votes and that indicates the state of the system, what that suggests is for the malicious party, they just need 1 extra vote, being they need 6 votes in total in order to change that state of the system. So going back to empirical measurements, again, we looked at the distribution of MKR across different entities and so on. And what we notice is that there's actually a very high concentration of MKR holders. And here is illustrating the top 10 holders. As you can see, the top 1 and 2 combined have an MKR holding in total of over 100,000 votes. And then on the other hand, you tend to get low voter turnout in these different voting procedures. In fact, the latest, one of the most recent executive vote only took about 45,000 MKR to win. And kind of borrowing a term from finance and stuff, this is what we call the high watermark, because that's essentially indicating this is how much votes you need for the next proposal to take over the current one, and in order to win and to change the state of the system. So we can imagine where there's a potential governance attack, and let's assume that the last executive vote was won with 45,000 MKR. Now there's 2 ways for the new executive vote to win. Either if with continuous approval voting, we have transfers of votes, so that means we only need 45,001 MKR votes to win. Or let's be conservative, if no transfer of votes happens, malicious party will need 90,000 MKR to win that round. And that means the cost of an attack, with everything considered, can be at most just under $50 million. Now, the consequences of a governance attack can be potentially huge. Well, these are the things that they can do to a system under the governance attack. For example, they can introduce a malicious coin as collateral. They can definitely try to change the permissioned logic within the median contract, because price feeders are whitelisted and they can elect or propose new price feeders who are part of the malicious group. And together, if they also change some key parameters like bar or age, they can directly impact the output of the reference price on the median. Imagine, because the bar number is currently set to 13, imagine they vote the bar size and reduce it down to only say 2. And if they happen to control one of the price feeders, then in a way they can just directly influence the output of that median price. They can also evoke the emergency oracle, which is again built in the median contract under the V2 version. And during emergency shutdown, they can cause serious consequences to the security of the network overall. And actually quite well timed, and I would say very relatable, is the fact that we do observe these hostile governance takeover that happen from time to time. And very recently, there was this hostile takeover by the Tron Foundation that essentially took over the governance of the Steam project by gaining enough the Steam token to overtake the original governance board. So it does happen. And it's very interesting to keep watching on that. And therefore, I think, in conclusion, we think that the version 2 of MakerDAO's Oracle has shown very significant improvement over version 1, especially in terms of addressing staleness. But there might be a bit too much power that's given to the off-chain relay server. And in general, we think it's still very much an open problem for this community overall to think deeper in terms of how we can design an Oracle system which is incentive compatible and to provide a better governance for everyone. And there's some really interesting and cool, promising protocols out there, which we also studied, including Chainlink and Ogre, where they have sort of like, for example, Schelling style sort of voting scheme, or like schemes where you reward and punish misbehaviors accordingly. So these are all very promising protocols to look out for, and it remains an open problem for us to, I guess, think harder and work on further. So thank you very much, everyone, for listening, and would love to hear your feedback and also any questions as well. Thank you.
Thank you very much, Catherine. We have time for a few questions. So we have microphones in the aisles. So if anybody has a question, would you like to make your way down to the aisle? I can kick off. Catherine, can you hear me? And Anika?
Anika, can you hear? Or shall I? Let me try to.
Okay, you won't be able to see us, but we can see you. Sorry if that's a bit creepy. One of the questions that reviewers had when we looked at your paper was the title of the paper generally refers to stablecoins. However, the work is mostly about a single collateral maker. So one of the questions was, how straightforward would it be to generalize this approach to a wider range of stablecoins or DeFi projects that rely on oracles?
Yeah, that's a fair question. And so we think that, I mean, it's important in order for us to carry out empirical measurements, it's important to pick up a representative stablecoin to study. But I think it's more important to try to sort of extract out the problems in general. And I think from Maker, what we learned is first two things. Aggregation amongst multiple price feeders are very difficult. And second, governance design is also very difficult. And I think those would be the two main takeaways for any stablecoins out there. And even though, you know, they have different, for example, aggregation algorithm, it doesn't always have to be the median price and so on. But what we realize, they all sort of encounter these sort of problems in terms of staleness, how representative they are, in terms of whether we can sort of elicit things such as truth reporting and so on from just the prices that we observe. So.
Great. So we have a couple of questions from the floor. Ishtvan's first.
Thank you. Really nice talk. I found it interesting that in Maker 1, the price feeder's identity was not known, but in Maker 2, you know who were the price feeders. What is your take? Which one is a better approach? Because if you don't know who to corrupt, then it might be reasonable. But also, to me, it seems like security by obscurity. But on the other hand, if you know who to corrupt, like Gnosis, and there were some other names, yeah, it's like an interesting trade-off between privacy of the feeders and bribing attacks on the price feeders.
For sure. And I think this is a great question. And I think you really hit the point in the sense there's definitely this conflict and you need to balance out and trying to see which one would makes better sense. I think the version 2 is superior than the version 1 just because they still maintain those 14 anonymous price feeders. And on top of that, they introduce more public partners that we know the identities of. I think certainly when we were looking at version 1 originally, it was a challenge because in our paper, we actually included a section that was trying to use hypothesis testing and trying to tell if, even if they're anonymous, whether we can tell just through the historical price behaviors, how much standard deviation they're reporting away from, and what can we infer from that based on the probabilities and hypothesis testing and so on. But it doesn't, you know, it's purely a statistical observation, especially given 2 years of history. The degree of confidence is not particularly high. Whereas right now, I think it's much easier to consider the quality of the price reports, especially if they're coming from public partners that we can verify the identities of. And I think definitely it makes sense for Maker when they launched the protocol originally to make those identities of those 14 oracles like anonymous, as you said, because there's a very high risk of bribery or collusions and stuff. So it's probably best to keep it that way. So I think right now a good, nice, balanced mix of both anonymous and public ones is the way forward. But you know, right now there's only been 1,300 transactions on the Ethereum contracts and about 1,600 on the BAT contract. So there's definitely a lot that we still need to wait and see whether, you know, there could be some potential manipulation that could happen.
Nice. I thought that all of them are public. Okay, then I misunderstood the design of Maker 2.
All right.
Yeah, they still keep some of the anonymous in the contract, okay. But nice. You now have a mix of people. So yeah.
Okay, great. We have time for one more question. Thank you.
I'm interested in the governance attack you mentioned. In particular, I'm wondering if you looked at other voting schemes. One thing that occurs to me is if you were to give an age weighting of the voters so that the ones that had been around longer would perhaps be overweighted in either linear or in some other fashion, then it would potentially allow for a protection against an attack by new malicious voters who could be ruled out in the protocol adjustment. Or any other sort of variation in the voting systems that would be more attack resilient.
Anika, if you want to take the question.
Oh, sure. Yeah, that is a really that's a really great point. I think there are definitely a lot of protections that could be implemented to to protect against this sort of attack. MakerDAO hasn't done any sort of thing as you suggested, and we've looked at a little bit into different systems, but haven't been able to do a similar level of analysis. So yeah, I think it's a great direction, I think, for MakerDAO to go in to kind of like balance different types of protections that could be put in place. And I think a system like that could potentially help with this this issue. And I think the way it's currently, where like voting power is completely in line with how much Maker you own, is good in a way because it can allow new voters to come into the system and kind of decrease the barrier to entry for a lot of new voters. But I definitely see what you're saying. I think that could be an interesting thing.
Yeah, and I think I just want to compliment on that. There's definitely already certain, like a lot of protocols out there, which is, I would say they put a lot more effort in just in terms of designing that incentive structure. So we definitely have things where you are weighting by age, and then you're also having things where like even the reward is being given to voters. For example, if they vote for the right outcome, that reward wouldn't be given immediately. It might be logged for a certain period, or it would be distributed and so on. So all these sort of interesting tweaks in the details, I think that would actually become very important to a particular protocol, because I think the devils are in the details, and in order to govern all these individual entities to behave in a way that we want to behave, I think those things definitely matter a lot.
Okay, without any further ado, thank you very much for the questions. Thank you, Catherine and Anika, for presenting, and let's hear a round of applause for our presenters.
Thank you, guys.